This is Jim Hendershot. We're ready to present lecture number 7 in this series of electric machine design course. And lecture 7, under lecture 7, we're going to discuss the design methods that are used to design machines, analytical design method versus the FEA design method. And for many years, for 100 years, classical machine design has been accomplished by using the formulas that have been developed over the years by many engineers and designers from many countries. The success and accuracy of these design methods has been validated time and time again and improved over the years by calibration adjustments based upon the test results of the machines that have been designed. And there are certain parameters in machine design that cause difficulties with respect to accuracy, and these have been addressed by several famous engineers who've developed approximation solution methods based on their test results. For example, the solution of the equivalent circuit equations for machines have been simplified by Alger and the Speed Laboratory at Glasgow. End winding leakage reactance is very all the reactance values are difficult to calculate accurately, and so a number of experts down through the years, Alger, Richter, Postnikov, and leakage reactance saturation by Norman, deep bar effects for induction machines by Ian Bolday from Romania. So these are very important contributions, and VNOT and Tricky have also contributed calibration factors to improve the accuracy of machines based on their extensive testing. One of the problems with the analytical machine design calculation methods is that, as I mentioned in an earlier slide, that magnetic flux densities are assumed to be uniform through each of the circuit cross sections, such as the teeth and the yokes. But and when you use classical methods, you have to assume that you certainly can calculate the flux densities in, if you have a tapered tooth, you can divide the tooth up into a couple of regions and calculate the flux density in each of the regions to improve it a little bit. The other thing that analytical test methods or calculation methods suffer from in terms of accuracy is leakage flux, where the flux is going to go where there's air gaps or where there's forced by saturation, forced by changes in the permeability of the steel due to saturation. So these effects have to be measured, or at least that's how they've been done in the past. But these analytical methods use classical magnetic field equations for calculating the flux magnitude and distribution within the magnetic circuit, but as we've shown, these can only be estimated. Leakage and the effects in changes of material permeability due to flux densities cannot be accounted for using classical field equations. However, these results from those methods are very useful because they're fast, and with the use, if you put those in Excel and things like that, you can do it, and solvers like that using computers, you can do very fast iterative solutions. But this process is used for initial designs and sizing machines, and for simple machines where there's no or very little flux leakage. But over the years, we have developed usage charts for acceptable data for average current densities and average circuit flux densities, and this certainly speeds up the design process. Each motor engineer, as I've said before, is invited to develop his own tables of acceptable current densities and circuit flux densities that are pertinent to the machines that his company builds and how they're cooled. And certain expert machine designers have developed certain unique solution methods for their machines, and they validate them with tests. But for very accurate analysis of the flux distribution and for inductance calculations and current densities and gradients, and if you have a number of conductors in parallel, it's very difficult to calculate the effects of proximity or the effects of skin effects without using FEA solvers. But the classical methods can be used in conjunction with FEA solvers as pre-processors to speed up the sizing and get into the ballpark, and then use the FEA to predict the final detailed results to get current density distribution, Q and D axis inductance values, torque output, of course, for torque speed curves, and losses, different kinds of losses, eddy current losses, hysteresis losses, to wind up with accurate efficiency results. And then, of course, it goes without saying that for thermal simulations, classical methods have been used for years for predicting the temperature rise in a machine using a lump parameter equations, but a 3D thermal solver gives much more accurate results. And the FEAs used then to refine the design and look at unusual circumstances. The finite element method of magnetic circuits greatly enhances the study of the flux distribution by dividing the cross-section up into smaller pieces of cross-section, including the surrounding air, to very small bits such as triangles for 2D analysis and pyramids for 3D analysis. The magnetic field equations are then solved for each of these bits, called mesh. We call those little bits of mesh. So to find out what the flux distribution is over a large cross-section, you break it up into a bunch of smaller cross-sections and calculate the average flux density in each one of those little bits in the mesh, and then you connect them all together to predict a pattern of a flux density through the large flux distribution through the larger cross-section. However, to make this accurate and to calculate the core losses this way, the correct material properties have to be inputted into the solver, and this is, of course, one of the biggest problems, is to get accurate material data. But by solving the field equations for each bit rather than the major circuit components such as yokes and teeth and magnets and coils, by, of course, the frame and the shaft parts are usually ignored, but they don't have to be. But so this allows the open circuit air gap flux distribution to be accurately studied, including flux leakage details as a function of phase current for motoring and generating. Flux leakage are in and around air gaps or through saturated portions of the magnetic circuit. The flux leakage is really caused by high currents in the electromagnet, primarily. According to a well-known professor and teacher of electric machines, Professor Dwayne Hanselman, he states that FEA analysis is not a practical tool to be used exclusively for the design of electric machines, but moreover to confirm or improve a machine design. And I certainly agree with him, and I think it's important to underscore this point that many young motor designers will try to begin a design of a motor using a FEA solver, and that is not the way to do it. You use an FEA solver to refine or improve or confirm the design of a machine. But to design a good machine, one must start with a sketch, which we'll talk about soon. In other lectures, we've shown this simple magnetic circuit several times. This doesn't look like a motor, but it contains all the components in a motor. And we have the yoke, or the C-frame steel magnetic circuit here, and we have a coil that's wrapped around part of that circuit that represents the electromagnetic phase coils in any machine. And then we have the air gap. And so as we've stated before, that the ampere turns, it takes ampere turns, current times the number of turns. It takes so many ampere turns to magnetize that iron. And it takes a lot more. It takes maybe 10 or 20 or 50 times the ampere turns to drive the flux through the air gap that it does to drive it through the iron, because of the difference in permeability of the air gap versus the iron. A simple flux density calculation would be done using classical methods, and that would be to, for example, here's that same yoke that has a coil wrapped around it, and we want to know what the flux density is in each part of the circuit. We want to know what the flux density is in the gap and in the different legs of the circuit. And those legs of the circuit, you can think of those as the yoke of an electric motor, or the teeth of an electric motor, the two tips of an electric motor, and basically B is a flux density, and we calculate the number of lines of flux from the ampere turns of the phase coil and the cross section of the steel, and that flux density can be converted to any other part in the circuit by ratioing the material cross sections. If for example, if we have one Tesla in here, and we make this half the cross section of that one, then we're going to have 2 Tesla flux density in this part, which would be too high, of course, you see. So the ampere turns, or the magnet, generates so many lines of flux, so that the flux density in a machine is that many lines divided by the cross section of the machine, and it can be proportioned from one cross section to the other. Such a simple circuit calculation can be sufficiently accurate for many machine applications. For example, it's certainly acceptable as long as the flux leakage isn't excessive, and as long as there's no saturation in this circuit. The only place you're going to get some flux leakage is around this air gap here. But if this gap is small enough, you're not going to get very much. So flux leakage in this case might be negligible. But if you have another pole close to this, or you have some portion of the frame that was close to this, let's say you had another piece of steel here, then you might get some flux leakage that, instead of going to the other pole here, it would jump across and into this some frame member that's close by. So that we couldn't calculate with analytical methods. You could only estimate it. You'd have to use finite element solution to do that. So flux leakage, if the flux leakage is not excessive, or if there's very little chance of flux leakage being possible through adjacent magnetic materials, then analytical methods will suffice. As long as there's minimum or very little saturation, then analytical methods work fine. if the circuit could be defined in the XY plane, in one plane, if it's not a 3D magnetic circuits, like hybrid step motors, the flux path takes an orthogonal path. It's in 3D, and so that would be very difficult to calculate using analytical methods. That's a case where FEA is very important. The transverse flux brushless machines or homopolar generators, these types of machines have orthogonal or 3D flux paths. So in those cases, they're being very difficult to calculate using analytical methods. It's more accurate to use FEA methods. And in fact, as a coincidence, those 3D magnetic circuits have a much higher propensity for flux leakage than XY plane magnetic circuits. So that's another reason why, because of the leakage analysis, end-turn leakage, things of that sort. Motors that have skewed rotors or stators, that is an accurate analysis of the effects of skewing a rotor for an induction machine or skewing the magnets or the stator in a permanent magnet machine. The effects of skewing, it turns out, can be estimated pretty accurately by analytical methods as long as you break the core length up into little slices. In other words, you kind of skew it in a step fashion, and you solve each one and knit them together and you can see the effects of the change in the back EMF wave shape when you skew a PM rotor. And you can do that in a two-plane or an XY plane analysis by really solving breaking up that skew into little short motors and solving each one and then knitting them together into a final back EMF block. But a FEA method, of course, displays that very accurately because it's a 3D problem. Analytical methods have been used for at least 75 years, and there's hundreds of millions of motors that are operating successfully without the use of FEA analysis. So it's always good to keep that in mind, that the old analytical methods, the tried and true classical performance formulas has served us well, and in the engineering community, and so don't be quick to toss out those methods. Also, one of the drawbacks of using FEA analysis is you tend to trust the computer too much, and you don't. The designer sometimes doesn't understand in detail how the machine works. So it's a good practice to size and model a machine using analytical methods, and then use a finite element method to refine your results, and then go back and, where appropriate, use analytical calculations to validate and do sanity checks on your FEA results if some of them don't make sense to you. This is an example of an unusual flux distribution in a machine. This happens to be a cross-section of the Toyota Prius motor. And these IPM machines, the performance can only be estimated using analytical methods. The final prediction of all the important results in a machine like this can only be analyzed using finite element methods because there's so many difficulties going on here. For example, what first thing you see is it's intuitively obvious that the flux density is not the same in all the teeth. That's somewhat of could be a surprising result for young, inexperienced machine designers. When you calculate a machine, you might assume that the flux density is the same for all the teeth that are over the top of any given pole, because they carry the flux intuitively. and using analytical method, that's the way we assume that all the flux coming from one pole, from the rotor, would go across the air gap and go into the teeth of the stator. So you would assume that that would be done uniformly. But you see, if you're controlling the current at some angle between the direct axis and the quadrature axis, and just to remind you, the direct axis is the center of the pole, the quadrature axis is in the center between two poles, so that would be this angle here. So the current angle isn't centered on here, and it's not centered on here either. It's centered kind of skewed. I don't know, where is the center of the current angle is right here, isn't it? So that causes the flux to move the flux from the magnet to move sideways or tangentially in this soft iron pole piece here. So there's more lines of flux from the magnets going through these teeth than there are these two teeth. That's what happens. So that affects the flux distribution in the yoke, and of course the teeth. Of course, not to mention the fact that these teeth have to be tapered, so the flux density is higher where the teeth are narrower than it is where the teeth are thicker. The other thing is study the flux distribution in the rotor. That's kind of weird and strange. You've got, remember, this magnet, if this is a north pole, that's a north pole. So every one of these pairs of magnets are the same polarity. So you've got the flux coming out of this pole, but for some reason it wants to favor going for that over that pole, and that's because of where this current vector in the stator is. So the angular location of the current vector at any point in time during the rotation with respect to where the magnet flux is affects the distribution of where that magnet flux go. Now we have another thing going on. We have these leakage paths that are inherent in the IPM machines, and those little webs of laminated steel, we don't like those there. They're there to hold this thing together. If we put air in there, then the centrifugal force on these magnets would put a very high stress on these little pieces here that holds it together, because there's nothing holding in the center. So the centrifugal force at speed on these magnets would cause this OD to expand out and rub on the idea of the stator. So the designer has put this little web of steel in there to give section modulus here to restrain the mass of this against centrifugal forces. That's why that's there. And the thickness of these little webs are also based upon not magnetics, but they're based on the yield strength of the material and the centrifugal forces on the masses that that has to be restrained by these little webs. Does the same thing as this. So consequently, you particularly in the case where you're forcing flux to go over and have a higher flux density over this magnet than that magnet due to the field. This is reactance. The permanent magnet flux is reacting to the effects of the electromagnet, and that's what causes all these flux densities to distort and to do what they do. So the only way you can analyze that is to use a finite element solver. How else could you predict this? Cogging torques is another area that is very important on PM machines for some applications, not all applications, but cogging torque is an open circuit torque. In other words, there's no power connected to the machines, not driven at all, and it's associated with only PM machines. Without permanent magnets, there shouldn't be any open circuit torques. If there's open circuit torques on a motor without magnets, then you've got a problem with the bearings. You've got flat spots on the balls on the bearings, or the rotor's rubbing on the stator. It's mechanically, physically rubbing. The OD of the rotor is rubbing on the stator, or it's rubbing on the winding end turns or something like that. That's the only way you can experience the effects of cogging torque on a motor that doesn't have magnets in it. Now you can estimate these cogging torques by analytical methods, and that can be very useful for relative analysis of comparing slot and pole combinations or the arc angle of the width of the pole. Also slot opening dimensions, and of course slot pole combinations. For example, let's just illustrate that for a minute. If you have a 4-pole motor and 12 slots, you have and if your pole arc is 2/3 of a full pitch, being 60 mechanical degrees, and if you consider that gives you the maximum cogging torque amplitude. And the reason is because the sides of every one of those magnets will line up with slots. So you have 4 magnets, you got 2 sides, that's 8 sides. And so all 8 sides of those 4 magnets will line up with 8 slot openings in the stator, because a stator with 12 slots has 30 degrees per slot. So 2 teeth is 30 plus 30, that's 60 degrees. Well, that's the same angle as a 2/3 pitch 4-pole motor, 60 degrees. So that means that every edge lines up. That has the maximum cogging torque. Now, if you increase the pole arc from 60 degrees to 65 or 70 degrees, your cogging torque is cut in half, because but the frequency's doubled. Now you only have one edge of a magnet lining up with a slot. And since there's 4 magnets, one edge is 4 slots, so there's only 4 reluctance alignment positions of the rotor to the stator. So that's just enough to show you what the effects of the slot and pole combination can be to minimize cogging torque. But precise calculations of this have to be done using FEA analysis, and there's cases where the cogging torque has got to be so low that FEA is the only way to do it. But there again, you should start your design with, it takes a long time to do an FEA analysis, so you should start your design using analytical methods. Go through the logic of selecting the right combinations and pole arc angles in the first place, and then maybe set up an Excel calculation using analytical methods to hone in on it, and then use finite element to refine it. Copper loss calculations are easily handled by analytical methods. That's pretty simple to calculate I²R losses and resistance in windings. That's not so difficult to do, except in the case where, like in induction motor rotors, during acceleration or startup, from time equals 0 to the first few milliseconds, the current density is not uniform in the rotor bars. So that's pretty tricky to calculate using analytical methods. You use finite element for that. The effects of the proximity effects and the effects of equal current distribution in parallel paths, that's very difficult and not very accurately predictable using analytical methods, unless you're really good and experienced at it, and you've developed your methods and calibrated them from careful measurements, or calibrated from using FEA solvers. In one of our lectures, we do provide the formulas to calculate if you need to use Litz wire, but that's based on skin depth calculations for the wire itself, and then comparing that skin depth cross-sectional area with the cross-sectional area of the conductor. So if the current only flows around the skin of a conductor, then at high speed, high frequency, you'll have an apparent AC impedance that's much higher than the DC resistance. DC resistance when the DC resistance measurement was taken under steady state conditions and involved the entire cross section of the conductor. But in very fast transient states, the current does not penetrate the entire conductor, but it only penetrates the skin. So there are analytical methods provided by the people who sell Litch wire to calculate what frequencies and conditions you need to use Litch wire. There are eddy currents that take place, and anytime you have changing currents or changing magnetic fields, you're going to have eddy currents generated. So you have these even in the phase conductors, and it's very difficult to calculate without using FEA methods. So circulating currents in delta connections and parallel path circuits, those can be analyzed pretty well using analytics, but there again, more refinement and detailed analysis results from FEA analysis. Another area that's becoming more and more important is to, particularly when your solver is connected to an inverter, and you can use these modern multi-physics simulators to input fault conditions in a motor or an inverter or both, and predict what the results would be. And you certainly need FEA coupling to those multiple physics simulation systems to predict the effects of faults and shorts in all kinds of machines. You know, you can have broken bars in an induction motor, and so the FEA simulation of the effects of that can go all the way to predicting how it affects noise and vibration of the machine, besides performance. And in the case of permanent magnet machines, if you get a transistor short or a ground fault short or a phase-to-phase short, you can use FEA to predict the results of that. This is becoming a very important topic for failure analysis of complex traction systems, for example. We've been asked to actually build motors with known faults in them that you can, turn-to-turn shorts and phase-to-ground shorts. We've actually built little test motors for dynamometer kits that have those faults constructed in them, and then external leads outside so they can be initiated, so that the students can model or test and compare with models what the results are of these kind of faults. Then for the purposes of this series of lectures, one of the most important things that we expect to learn out of this is how to optimize the rotors for these three different kinds of machines. And certainly FEA analysis is going to be very important to accurately undertake those optimized designs for induction machines. And we want to study the transient currents and proximity effects. We want to study leakage reactance, and it's very important in induction machines that are inverter fed, as I've said before, to balance the cross-sectional area of the rotor to have acceptable current densities in the bars, and yet not take up so much space that we don't have enough cross-section to carry the flux for peak torques. Because to get peak torques out of induction machine, we've got to have high magnetizing currents, because it's still a shorted turn. We can't adjust the current like we can in a stator. We can reduce or increase the current that it takes to produce torque by changing the number of turns. We can add more turns, and this gives you lower current at peak torques. You can't do that with an induction rotor because there's only one turn per coil per phase. That's all there is. So the only way to adjust the field is to adjust the current. So the current density goes high at peak torques, and so does the flux density gets high at peak torques, because the flux that's created by that ampere turns is much greater, and it's using the same space in the rotor that the copper uses. Then, of course, for flux vector control of all these machines, accurate predictions of the D and the Q axis inductance are very important. And in the case of the reluctant synchronous machine, the ratio of the saliency is very important, and it's a direct function of this D and Q axis inductance. The number of flux barriers and the flux carriers and their size and proportions determines what that D and Q axis ratio can be. Is it 2 to 1, or is it 5 to 1, or 7 to 1? So the design of the barriers and the carriers of flux in the RSM are so critical, and the only way to do that is using finite element solutions. You can start with a cross section in a model. You can start with a proportion, but the only way you can determine what the final results of that is to calculate it. As a matter of fact, the University of Wisconsin, in conjunction with Emerson Electric, Gary Horst at Emerson Electric, they did an awful lot of work on modeling and building and testing a variety of reluctant synchronous rotors with various proportions of flux carriers and flux barriers, proportions meaning their thicknesses, to determine some guidelines as to what you could use. So this saves. This is a very good reference material. It's in a paper published by University of Wisconsin, the WEMPEC group, and that's very helpful in having a place to start to figure out how many flux barriers and carriers you need and their configuration and proportions. But you still have to use your own FEA analysis to predict the results. Then the PM machines, this last class of machines, the permanent magnet machines that are either surface mounted or internally mounted. One of the most important things to analyze is the demagnetization of these magnets under operating conditions. And yeah, there's some graphical methods that have been used for years. My recollection of them, they were first presented in a white paper written by Alan Bradley, a well-known magnet vendor of the past. And they had an application engineer who eventually became president, CEO of TDK Magnetics, as they bought Alan Bradley's magnet division. His name was James Gallhart, and he wrote a classic paper on how to use permanent magnets graphically from the BH data, and we're going to study that in a later lecture in more detail. But as part of his white paper, he showed how to graphically determine what the demagnetization ability of magnets are. And that's a very useful graphical analytical method. But in the end of the day, you still have to use finite element to accurately predict that based on temperatures and demagnetizing currents, particularly with the neodymium magnets that are so temperature sensitive. The other thing is that neodymium magnets have a very poor thermal characteristic with respect to the B. The flux density varies as let's see, I believe it's like 0.10 to 0.12% per degree C, elevation and temperature, you lose in B. And to make matters worse, it's not even linear. At some point, there's a knee of the curve in the second quadrant, so it's not even linear. So that's a big problem that is very hard to calculate using analytical methods. So to predict what your flux is at different temperatures in your PM machine, so you really need to use finite element for that as well. And then the losses, we can, as we've already said, we can estimate what the rotor losses are, and it's much easier to estimate the iron losses in a stator than it is a rotor. It's much tougher in the rotor because of the motion of the flux and the concentrations of where the flux densities are, and the motion of the dφdt in the rotor as the rotor rotates because of the slot openings in the stator, or because of the PWM of the voltage from the current, the resulting current ripple from the stator and the slot openings, and this makes it very difficult to calculate the losses in a PM rotor. So you need to use a time-stepping solution using FEA to study those losses. Inductance calculations, that's another area. There's formulas for D-axis and Q-axis inductance calculations. They can be estimated using classical electric machine analytics. But the problem with that, with those solutions, is saturation of the iron. Open circuit inductance calculations can be pretty accurately estimated using classical electric machine analytics. But as soon as you start to as soon as the permeability of the magnetic circuit starts to change, now your inductance values aren't accurate anymore. So the only way to predict D and Q axis inductances in a saturated circuit is using finite element analysis. And this becomes very important in all three of these machines because of the popularity of D and Q axis current control. The final area where finite element is essential is in the thermal analysis. Up to about 10 years ago or so, there was very little in the literature and no technical journals or IEEE papers or books on the thermal analysis of electric machine. The best we could determine is the technology on this subject, and the trades was kept by trade secrets by suppliers, by people like GE and Westinghouse and Siemens and Alstom. They knew a lot about the thermal characteristics and the heating of the internals of electric machines and how to cool them. But what they learned, they determined by test, and they kept all this a secret. Some years ago, a professor by the name of Dave Staton from the UK changed all this. He developed a computer simulation tool that uses I think it's a 20-node lump parameter method. And so ever since he developed that product while he was at Control Techniques, owned by Emerson, and he left there and started his own company, and he sells his software, and he published many articles on this topic, and has tried to demystify this a little bit and teach us a lot about how to use the lump parameter method to analyze the thermal analysis of machines. But more recently, Infolitica, a company in Canada, has introduced a 3D finite element thermal simulation tool for modeling all of these machines. The lump parameter method offers a faster solution, but the 3D FEA solver is potentially more accurate. Finally, the motor and drive behavior, the behavior of a system of a motor driven by an inverter and a controller. You can link FEA field simulations with other tools such as MATLAB Simulink, PSpice, and DSpace, and Opal RT has products that add complex control circuits. But without proactive FEA link of actual motor field simulations, those above mentioned control simulation tools, high performance seem to be very difficult to design today using traditional analytical methods, if not impossible. Here's some examples of some results of using finite element solvers there. A cross-section layout of a machine is where every design begins, and many solvers have a template-based front ends that enable you to start with a template. And an experienced designer can select tooth widths and slot depths and yoke thicknesses and things like that, just based on the proportionality of these scaled sketch layouts is very important for machine design. I can't underemphasize this. I must overemphasize the importance of a scaled layout in machine design. Current distributions in the conductors. This is an induction motor at no load. You see there's a lot of current flowing in the stator, but very little in the rotor. Where all that stator current is used to magnetize a circuit to create those flux lines. You see those black flux lines. That's what the current in the stator does. But it's not producing any torque. It's only producing a tiny little bit of torque, so you see some red spots right at the slot openings in the rotor bars, and that's the torque-producing current to overcome the friction in the system, the windage, the bearing friction. Eddy current and hysteresis losses in the iron you predict, and have a color-coded plots of those, and you can read the detailed data. Flux distributions in a highly saturated circuit. This happens to be an induction motor at peak torque, and as you can see this tells you where the flux concentrations are. It's not uniform in the teeth or the stator yoke. So information like this would help you to change cross sections if need be. This is peak torque of that Toyota Prius motor, more saturation in the teeth and around the magnets. Torque speed curves are performed quite accurately using batch files of FEA solutions at different specific load and speed points, and then knitting them together using spline fitting algorithms. You can predict the back EMF using finite element solvers. This is an example of a solution with no skew and with skew, and in the background is the idealized sine wave outline that you're shooting for. Winding patterns. Oh, it's very difficult to come up with windings for some motors. Not the number of turns per coil is one thing, but where do you put the coils? If you have a 24-slot stator, there's and 20 poles, there's 7 different possibilities for putting those coils in different slots to get balanced winding. So you need to study all the possibilities and pick the one with the highest winding factor, and a lot of pre-processor front ends on finite element packages provide this service. And then they also, I'm a big believer of pictures. Pictures help. We study and think about machines analytically and with formulas and all the classical descriptive methods, but they're still mechanical machines, and to get your arms around a design and understand what's going on, you need to see pictures. So here's a couple of, I love the ability of finite element solvers and other solvers to be able to give you a graphical picture of what the phase windings look like, where the coils are, where they're located. It's very helpful. That ends and concludes this lecture. Thank you very much.